Every single day, our most massive global systems, things like power grids, logistics networks, smart cities, they all kind of teeter on the edge of failure because of one fundamental mathematical problem. Tiny errors compound over time. Just a fraction of a decimal point lost in a prediction today can literally become a catastrophic failure a week from now. Well, let's jump right into this explainer because we're going to explore a radical solution to that exact problem. We're looking at why reversible deterministic operators running on real NVIDIA hardware matter profoundly for the real world. We are moving far beyond some simple physics experiment here. We're talking about establishing a flawless foundational bedrock for predictable global systems. So, pose this question to yourself. What if reversibility is actually a proxy for system stability? Instead of viewing this as just a mere simulation of plasma, we really need to look at this test as a concrete computational primitive, one that demonstrates absolute long-horizon reliability. Think about it like this. If a computational system leaks data or rounds numbers incorrectly as it moves forward, it is mathematically impossible to reverse it perfectly, right? So when a system can evolve forward into total chaos and then flawlessly reverse backward to its exact starting point, it proves without a doubt that it isn't compounding those tiny hidden errors. This reversibility is essentially the holy grail for managing massive, complex infrastructure over long periods of time. Okay. Let's get into Section 1, the reversible plasma primitive. To really grasp the magnitude of this, imagine stirring a drop of milk into a cup of coffee, letting it swirl into total chaos, and then mathematically unstirring it back into a pristine, perfect drop. In computer science, achieving that without the system just completely fracturing is incredibly difficult. And what we're looking at brilliantly illustrates the rigorous engineering behind this execution. We're pulling and running a digest-locked Docker image directly inside NVIDIA Build. Now, digest locking acts like an absolute digital fingerprint. It guarantees that the compute environment is 100% identical every single time you spin it up. It completely eliminates that old, well, it works on my machine headache, ensuring true cross-machine reproducibility. This is not some theory in a white paper, it's tangible, executable code. So we start with a swirling plasma-like field on a 128 by 128 grid using a precise time step of 0.02, evolving it forward for 400 steps and then backward for 400 steps. What makes this a massive achievement is that we get identical, verifiable results across vastly different enterprise GPU architectures, H100s, A100s, L40Ss, and T4s. Look, achieving deterministic behavior across different hardware is notoriously difficult, simply because different microchips handle floating point math slightly differently at a microscopic level. Forcing absolute agreement between a massive H100 and a T4 chip, that requires an unbelievably robust mathematical foundation. And the absolutely crucial point here is this exact L2 reversibility error, isolated after 800 total steps of complex swirling dynamics. It sits at 0.0939. To put that into perspective, in standard simulations, after just a few dozen steps, the mathematical rounding errors compound so aggressively that attempting to reverse the system just yields pure garbage data. The fact that this error is a hair's breadth away from absolute zero represents an incredibly tight return to the initial state while fully preserving shock stability. It's the physical, numeric proof that the underlying foundation is completely, entirely stable. We also measure an incredibly low energy drift value of 0.286. What this implies is really fascinating. You see, sometimes simulations basically cheat by applying artificial smoothing or numerical diffusion, essentially forcibly calming the system down over time so the math doesn't just explode. An energy drift this low means the system isn't bleeding out its momentum. The chaotic, swirling energy, the structural integrity of the folds and stretches, it all survives the entire 800-step round trip completely intact, and we don't have to artificially hold its hand to make it happen. Moving on to Section 2, dismantling the critiques. Let's address the skeptics head-on using hard hardware metrics. The first critique we usually hear is the claim that this is just a toy simulation, but honestly, toy simulations simply do not produce deterministic, reversible transport with perfect shock preservation across multiple enterprise GPU architectures. A toy breaks when you push it under extreme pressure. This substrate, running on real NVIDIA hardware, digest-locked and cross-hardware reproducible, holds perfectly stable under the most brutal, enterprise-grade scrutiny imaginable. It is built for reality. Next, people might argue, well, reversibility doesn't matter in real systems because time only moves forward. But that fundamentally misunderstands the math. Reversibility is a proxy for forward-moving stability. If a simulation cannot cleanly reverse, it means it's secretly accumulating tiny, hidden errors as it calculates forward. If you want to predict a catastrophic power grid failure 24 hours in advance, you need to know with absolute certainty that your simulation isn't just compounding rounding errors. Reversibility guarantees your predictions are fundamentally stable. Then there's the claim that this is all just numerical trickery. But think about it. If this were a simple math trick, the simulation would immediately fracture and shatter across the different floating point architectures of the H100 and T4 GPUs. Surviving that incredibly complex translation between different physical silicon chips without breaking determinism is practically miraculous in computer science. It proves beyond a shadow of a doubt that this is a true structural breakthrough, not just some clever illusion. Critique number 4 assumes this foundation doesn't scale to massive systems. Actually, scratch that assumption entirely, because scaling here isn't hypothetical. The exact same operator is already driving public, reproducible, trillion-token transport modeling at scale. It's actively powering the trillion-token scaling explorer. This represents a total paradigm shift. When you build a system on a flawless, reversible foundation, you aren't fighting exponential error rates anymore. Scaling up simply becomes a matter of adding more compute power. Finally, there's the critique that a plasma simulation just isn't real-world enough. But you have to realize, this operator acts as a foundational domain-agnostic substrate. Think of it as a universal engine for complex flow. Because it is fundamentally just a perfect mathematical model of transport and dynamics, we can take the plasma out of it entirely and plug in traffic, electricity, or supply chain logistics. It generalizes by design to unlock entirely new classes of capability infrastructure. Which brings us perfectly to Section 3, Real-World Infrastructure Scale. Let's look at that real-world impact. The leap from a 128 by 128 grid to the entire global economy is incredibly direct. Because this primitive is a universal engine of flow, it serves as the bedrock for massive systems. We are talking about accurately predicting load propagation in national energy grids to prevent cascading blackouts. We're talking about modeling shockwave cascades in smart cities to optimize traffic flow and stabilizing timing-sensitive logistics networks to prevent global supply chain routing failures. The core mathematical challenge across all of these domains is exactly the same: managing complex, cascading systems without compounding errors. This operator is literally the foundation for stable, interpretable, large-scale systems modeling. By ensuring identical, predictable execution on every single run, we completely eliminate the uncertainty that traditionally plagues trillion-token simulations. Imagine building a digital twin of an entire city's infrastructure. When it runs on a deterministic, reversible substrate, you can trust its predictions over incredibly long time horizons. Hardware certainty completely replaces guesswork. You are calculating the future with absolute precision. Finally, let's wrap things up with Section 4, the Oikonomia Platform suite. All of this hardware-verified architecture connects directly to a much larger public ecosystem designed to redefine global computation. The plasma simulation, that's just the initial proof of concept. The platform provides the full deterministic substrate, the reversible operators, scaling behaviors, and domain-level applications. But honestly, the most crucial part is the radical transparency. You do not have to take my word for any of this. The public Docker artifacts and the validation methodology are available at oikonomiaplatform.com for independent verification. The whole shebang is ready for deployment right now. So, I want to leave you with this thought to ponder. If a reversible computational primitive can fundamentally eliminate unpredictable failure cascades, how will this deterministic substrate redefine our most critical global infrastructure? When we finally stop fighting computational drift, what impossibly complex systems can we confidently build? Remember, this isn't theoretical math. This is the reversible plasma test, executed flawlessly on real NVIDIA hardware, entirely reproducible across architectures, and available today as part of the Oikonomia Platform Validation Suite.